Hello everyone, and welcome to the start of Chapter 7, which is going to be all about exponential and logarithmic functions. In this section, we're going to be looking at exponential models, and before we look at some exponential models, I want to make sure that we're all on the same page of what an exponential model is compared to stuff that we've looked at in the past. So on the left, we see y equals x squared. This looks very familiar to us. We've been working a lot with these. These were polynomials. On the right, we see that our exponent is a variable as opposed to our variable being as a base. So these are what we call exponentials. So our exponent is going to be where our variable is as opposed to just being the base and then having an exponent on top of that. So if I'm looking at these exponentials, these are going to look different than polynomials. Our general form is going to be a b to the x, where a kind of helps determine our shape, and then b is going to help us determine whether we are growth or decay. If a is greater than 0, so we are looking above the x-axis, and b is greater than 1, we're going to be looking at an exponential growth, just like this blue guy right in here. Now, if a is greater than 0, again, above the x-axis, and b is between 0 and 1, aka we're looking at a fraction, we're going to be representing an exponential decay. So it's going to be represented something like this red function. If b was negative, then we would kind of transfer that over to a and make a negative and just flip this whole thing upside down. So really we just have to worry about, okay, is my b greater than 1, or is it a decimal? Is it something between 0 and 1? In either case, our range is going to be everything above the x-axis, presuming that we did not shift anywhere up and down, and then our domain is all real numbers. We can plug in any sort of number. Now, depending on our situation, there are certain domain restrictions that might make more sense, such as if we were dealing with time, we wouldn't be talking about negative time, but in a general sense, we are looking at domain being all real numbers. So let's take a look at a couple of problems and see if we can identify if they are growth or decay, and then what our y-intercept is, which, if you think about it, is going to be where time is 0, so realistically, where we're starting. So if we look at a over here, y equals 3 and then 4 to the x. To determine if we're looking at a growth or a decay, we're really looking at, well, what number has that exponent of x. In this case, it's a 4. 4 is greater than 1, so this is going to be a growth. When time is 0, this 4 to the x is just 1, so my y-intercept will just be 3. If I look at b, I'm looking at 11 times 0.75 to the x. Again, I'm looking at what has that exponent of x. In this case, I'm at 0.75. That is a number between 0 and 1, so here we have a decay. And if my time was 0, this thing would be 1, so my y-intercept would be 11. Now here's words instead of a function given to us. So you put $2,000 into a college savings account for 4 years. The account pays 6% annually. Now, if you're putting money into a savings account and it's saying that we are paying interest, it's a pretty good indication that we're talking about growth. Otherwise, it's not a very good savings account. At time of 0, at our initial investment, we put in those $2,000. So we can identify growth or decay, and identify where we kind of started out with, whether we're given a function or if we're given kind of a word problem. Now, if we're going to be modeling, we're going to be writing some functions. These are sort of the standard, what we always kind of go off of. Lowercase a is our initial amount, what we started with at time 0. And then we're going to do either 1 plus or 1 minus our rate as a decimal. It's very important that your rate is a decimal, since 1's kind of representing 100% as a decimal. And then t is our time. A of t is just the amount after that amount of time. So, like that savings account, you invested a certain amount. After X many years, A of t would represent how much money we have in our account. So let's give this a try and see what we come up with a couple problems. You open a savings account that pays 4.5 annual interest. So again, we are getting interest. We're looking at a savings account. We're looking to gain money. If our initial investment was $300 and you make no additional deposits or withdrawals, two parts. We're going to look at how much money will be in the bank after 5 years, and then we're going to see and estimate how many years it'll take for the account to grow to at least $500. So for part A, we're looking at a growth. So my initial amount is that 300. I've got 1 plus my rate as a decimal, move over my decimal twice, to my time, which in this case is 5. So I've got 300 times 1.045 to the 5th. And if I plug that into my trusty calculator, we see we have approximately $373.85. Money only goes to 2 decimal points, so we'll kind of leave it at that for our amount. It's not bad for not doing anything with this money for 5 years. You get almost extra 75 bucks. Now, what if you were saving up for something and you were keeping with this account and you were wondering how many years is it going to take for this account to grow to at least $500? Now you have two options. You can either work with the same function that we were looking at above and just manipulate that 5 to pretty much guess and check, or a really nice way, presuming you have a graphing calculator, is to plug that function in for your y. So we're kind of graphing it, but instead of actually putting in my graph, I'm going to look at the table and take a look at my values. Just make sure that when you put it in here, we go back to x, because we want to manipulate the amount of time. We don't want to plug in 5 and it just tell us a constant value. So I'm going to take a look at my table. We've got some values here. Looking at 10, we're only at 465. And at 12, we reach a little bit over 500, 508.76. So I'm going to say about 12 years. And you could guess and check by manipulating that 5, but if you have graphing calculator, it's really easy to, until we solve these for real, just plug it in, have your x for time, and take a look at your table. Now what about the reverse type situation? The initial value of a car is $30,000. After 1 year, the value of the car is $20,000. Estimate the value of the car after 5 years. So I'm going to recommend that you find the rate. Sometimes it can be obvious depending on the problem. Like if it's a half-life problem, you know your rate is 0.5. Sometimes it's a little bit less obvious. In the cases where it's a little bit less obvious, you can always set up an equation for yourself. So we have our amount after a certain amount of time is this 20,000. My initial is 30,000. I have some sort of rate that 1 plus, 1 minus. We know it's going to be a 1 minus, but it's going to be something. And this says after 1 year, so that's my time, 1 year, my value is that 20,000. So r to the first doesn't really do much for me, so if I divide both sides by 30,000, I get that my rate is 2/3, or we'll just approximate it as 0.667. If you wish to use a full 2/3, by all means, go ahead. Now, I want to know the value after 5 years, so I don't know this. My initial value, still that 30,000. My rate we determined to be 0.667. And then my time is 5. So plug that into the calculator. So we've got 30,000.667 to the 5th. And we get that it's only worth a little bit less than $4,000. So my value after those 5 years, we have $3,960 and about 50 cents. Had you used the full 2/3 instead of rounding your decimal, you'd get about $39.50, so about $10 off, but I'll be able to tell from your work, you know, if you're off by a tiny little bit, which $10 isn't much when we're talking about the value of a car. So that's exponential models. We'll look at this a little bit more in class, and I'll see you then.